To start the thermal analysis, we first need to find and check out the master M-Card data from Teamcenter. We go into the folders directory and perform a search for EBSD, which is the name of our device which we'll be soon bringing to market. Many engineers have contributed to this dataset recently, so we can check changes and ensure the latest revision is being used for thermal analysis by looking at the assembly properties. Once we're satisfied this is the correct revision, we can open the model in NX. Here we can see the complex assembly and the part structure on the left-hand side. This assembly is in the latter stages of the design cycle, so much of the design is finalized. Rather than considering the entire model, let's zoom in on the main controller board near the rear of the unit. Here we can see the board in full detail, along with all the electronic components which have had their positions accurately placed by the E-Card M-Card Collaborator functionality via Expedition PCB layout. A total of 847 parts are reported, many of which are unnecessary for a thermal analysis. Because of this, we'd like to use NX functionality to temporarily suppress many of these components to save on simulation time. We can control component states by using suppression controlled by expression. We type flow EFD as the control expression. Next, we go to the NX expressions in the Tools menu, and we see we have a flow EFD expression with the value of 1. Changing this to 0 will force the previously selected components to become suppressed. In this way, we can use NX functionality to quickly disable selection sets for the purpose of analysis. The main FPGA under the heatsink dissipates 50 watts, so an active cooler is required. An NX embedded thermal analysis has already been created on this assembly, and by zooming out we can see the extent of the computational domain. Several analysis boundary conditions have been applied, such as material definitions on the heatsink and fan. A flow EFD fan boundary condition is present on the cooler fan. Contact resistances and 2 resistor features are also present. We'll come to the analysis specifics in a separate video, but for now, let's load the results and take a look at the heatsink temperature. We can see the min-max values and the hotspots on the surface. The flow generated by the fan can also be visualized and animated. A major benefit of having an NX embedded workflow is that changes can be made quickly and efficiently using pre-existing tool knowledge. For instance, let's make a synchronous change to the heatsink. We open the part, find the Move Face command, and edit the pin height upwards by 20 mm. We then confirm that this is indeed the new design intent. The heatsink is saved, and going back to the assembly, the heatsink has changed and the fan position is updated due to assembly constraints. We've already solved the updated heatsink revision, and we can see the temperature results of the change. The flow is also updated, and we can see air leaving from lower in the pin stack. But how do we know if this design is better? What's the delta from the base case? Let's now compare simulations using built-in flow EFD functionality. We select the plot orientation and adjust our scale legend to ensure consistency. We can see that the taller heatsink gives an FPGA temperature of 79.57 compared to 80.49 for the base case, only a 1 degree C change. The fan flow rate is largely unaffected also at 5.5 CFM. Under these circumstances, moving to a larger, heavier, more expensive heatsink probably isn't worth it. Let's bring back the suppressed parts with a change to the NX expression again. Now that we've run some upfront design space exploration simulations, let's run a fully detailed assembly to verify our design. We can see the complete assembly with 847 parts here with a thermal simulation. This run requires more mesh and a longer solve time to converge, which is the trade-off for better fidelity. We've now completed our sub-assembly simulation and are happy with the design changes. Let's commit the updated assembly back into Teamcenter as a Rev B of the design. So, as we've seen, there are many benefits to implementing a PLM managed workflow for thermal analysis, ranging from mitigating data safaris, quick CAD simplification, and rapid design change comparison.